In case anyone here isn't familiar with Donaldson Company, we've been solving customers' complex filtration challenges for over 100 years. We were founded in 1915 by Frank Donaldson Sr., who invented the first filter for a tractor engine. Today, we're one of the largest providers of unique filtration technologies. We excel at producing high-quality filters and components. We pride ourselves on having a global reach and a local touch. Our world headquarters is here in Bloomington, Minnesota. We have 56 manufacturing plants and 22 distribution centers around the world. So as you know, battery manufacturing is a relatively new and rapidly evolving industry. For over a decade, though, Donaldson's been at the forefront of lithium-ion battery manufacturing, providing critical vent systems to 6 major U.S. facilities and a significant number of others throughout the world, including China and the EU. We're also starting to see manufacturing lines come on for battery energy storage systems. The BESS systems is a growing area that we're getting involved in. And there's more ways that we're getting involved in the industry and staying in tune with the industry, including our membership with NAPBAT, the National Association for Advanced Transportation Batteries. We participate in 5 different committees, including manufacturing, education, recycling, regulatory, and lithium battery safety. And with that, I'm pleased to introduce our featured speakers today, Neil Young and Chris Perot. Neil's a territory manager with Donaldson out of Kansas City. His territories include Nebraska, Kansas, Western Iowa, and Western Missouri. He has over 14 years of experience in the air quality control industry. Prior to joining Donaldson, he spent 10 years with a large industrial air filtration supplier working across many industries. Neil holds a bachelor's degree from Northwest Missouri State University, and he's also Lean Six Sigma Green Belt certified. And Chris is an industry segment leader with Donaldson. He's been helping customers improve their industrial filtration equipment for over 30 years in the US, Latin America, and in Asia. He's spent time implementing solutions for many plants in the ferrous metals, non-ferrous metals, and rock dust applications. He's currently focused on the lithium battery market and its associated supply chain from mine materials all the way to finished batteries. Chris holds a bachelor degree from Rockhurst University and an MBA from University of Missouri. Turn it over to you, Chris.
Hey, thank you, John. I spent a lot of time working with the battery market, and like Neil, I'm looking forward to talking with you about it today. Kick things off, we'd like to start out by asking you your experience in designing dust collection systems for battery manufacturing. So please select the reaction emoji that best aligns with your experience level. We'll wait for you to do that.
Oh, looks like we've got a few experienced folks and some with none. So you got a pretty wide spectrum here, Chris.
Diverse crowd.
Yeah, mixed crowd. So
sure you
have something to offer everybody.
Thanks, everybody. Okay, let's start things off by talking about the basics of lithium-ion batteries. In electric vehicles, lithium-ion is the most popular rechargeable battery chemistry used in North America today. Describing the image on the right, small lithium-ion cells act like individual powerhouses. They're grouped into modules to boost voltage and capacity. These modules are then seamlessly stacked and integrated into a larger battery pack. This forms the car's central energy hub that finally connects to the chassis to power the vehicle. So here are 3 of the main types of lithium-ion battery cells. Prismatic cells have a metallic container with a rectangular geometry. Cylindrical cells are rolled like a Swiss cake roll or jelly roll, as some people say, resulting in a wound cylinder. These have the general appearance of what you put in your television's remote control or your flashlights at home. Then pouch cells use an electrode stacking method to provide a thin, compact, flat shape. These look like a Hershey bar without the exterior paper wrapper. Here's a cross section to show what is in a battery and the materials that are going to be captured. The cathode on the bottom left there was in a slurry coated onto the current collecting aluminum foil. It contains lithium, nickel, manganese, and cobalt. The anode, top right, was in a slurry coated onto copper foil. It typically is graphite. Those slurries were mixed with a PVDF binder to make them stick. And lastly, there is a separator material that permits electrons to pass back and forth and avoids short circuiting. Here's an overview of the manufacturing process. The blue dots indicate where dust collection is required. It's not hard to understand, but it has many steps, so we'll go through them now. Let's start with the manufacturing process for slurry mixing. Slurries are made by mixing active material, binder, and solvent. Dust-free mixing of cathode and anode slurries is essential for safe electrode production. Dry material and mixing processes can potentially generate airborne submicron particulate. This particulate can compromise both employee safety and potentially the quality of the end product. So coating and drying. At this point, the electrode slurries are coated evenly on copper and aluminum foils, then gently dried under controlled air to create a smooth adhesive layer. Clean air is paramount. Dust and fumes disrupt coating. That could potentially lead to uneven mill thickness of the deposited energy materials on the electrodes. This in turn can compromise battery performance and safety. So calendaring is compressing a material between rolls to make it thinner. This process helps create a uniform thickness and to densify the electrodes to a target value, which is crucial for optimal battery performance. From this point, the electrode materials are slit from larger parent rolls into smaller child rolls. This will allow the formation into different battery form factors down the line. Here we can have recoverable scrap and potential for flammable fume. As before, we need to continue a pristine particulate and fume-free environment. And finally, we have electrode cutting and cell assembly. For pouch cells are laminated and stacked. Cylindrical cells components are wound into a roll. These processes may use laser cutting and seam welding. This can generate metal fume and fine dust particulate of lithium compounds, cobalt, and nickel. Here, high volume production requires a high capacity dust and fume collection system. Also, fire mitigation should be considered. Also, in this part of the process, we encounter aluminum and copper foil scrap. For cylindrical batteries, this has the nature of metallic Easter grass, very appropriate considering the season. And for pouch cells, electrode notching creates what looks like large foil confetti. These contaminants need to be removed before the dust via cyclone or other mechanical separator to maximize production uptime. In summary, battery manufacturing generates both dust and fumes. Dusts are often fine, dry, lightweight, but there's often a lot of it. And fumes can be flammable, exposing facilities to the risk of costly downtime. So it is important to keep in mind that both dust and fumes may present a fire and explosion risk and may be hazardous if breathed in. We aren't going to talk about combustible dust a lot in this webinar. It's a pretty complex topic in itself, but we will circle back to it towards the end of the session. For now, just know that these dusts may be combustible. We have a webinar planned for June that's focused just on lithium-ion battery recycling, so we won't spend too much time on this today. However, for now, know that it is essential and is an emerging market in the US. We can no longer be dumping batteries with these essential metals into landfills, obviously. We need to recapture as much as possible because we will need way more batteries than we currently can build with mined materials in North America today. In this photo, you'll see disassembled lithium-ion batteries. For those with labs, it is important to note always wear personal protective equipment and limit exposure. Consider lithium on par with lead, but not as understood as it is used in emerging technologies. So there are many important reasons to control the dust generated during the battery manufacturing process. Here are some to consider. Safety first. Dust and fumes generated by battery manufacturing can have adverse impacts on employees in the short and long term. It must be controlled. Battery internal components can be adversely impacted by contamination that could lead to malfunction or even worse, thermal runaway in finished batteries. Clean air for protecting the environment and to support sustainable operations, and the cleanliness to assure a world-class facility of mass production and extreme quality. And now that you know a bit more about batteries and how they are manufactured, Neil's going to talk with you about the basics of dust collection systems.
Thank you, Chris. So what we're looking at here is a typical diagram of a typical dust collection system. You have a fan which creates an airflow that is used to capture dirty air with a hood and then convey that material through a series of ducts to a dust collector. Here, the particulate is separated out and clean air passes through the filter media to the fan where it's discharged to atmosphere. It's common in battery manufacturing to have a secondary HEPA after filter after the dust collector as well. Commonly, that's placed between the fan and dust collector. One important thing to note on these systems is that they are a sum of individual parts that are designed specifically based on the characteristics of the application. If one component is poorly designed or modified, the entire system is affected. So when we design a system, there are many factors that are considered. The publication shown here is the Industrial Ventilation Guide, which is the go-to resource for proper system design. The vent manual is written by the American Conference of Governmental Industrial Hygienists, or the ACGIH, which is a nonprofit scientific organization that advances occupational and environmental health. They offer multiple courses throughout the year on system design using the vent guide as a textbook. I've attended these courses myself, and Donaldson has a few experts who are instructors. These guidelines are considered by most in the industry, including OSHA, to be the standard for proper ventilation design. Things that we consider when we're designing a system include the material that's being collected and the properties of the dust, the application that's being utilized, the process conditions. Is it humid? Do the workers use personal fans? Does the facility have conditioned air? What are the hours of operation? Is the system going to be used continuously or intermittently? What are the total airflow requirements? What local or environmental restrictions exist? Is there compressed air available? Does the collector need to be located inside or outside? What are the footprint and height requirements? Has the dust been tested for combustibility and flammability? If it is, what NFPA standards would apply? And does the plant have expansion needs that we should consider when designing the system? So as you can see, there's a lot that goes into a well-designed system, probably more than most people realize. Something to really think about as you're designing a new system is the orientation. So what you're looking at here is a hypothetical view of a vent system for a lithium-ion battery facility. The centralized orientation is advantageous as the dust collectors can be in one common area. And the benefits of this is it keeps the hazardous dust off of the factory floor so that you maintain electrode integrity. It keeps the dust collectors away from the people working in these areas so that limit exposure. And it facilitates efficient and focused inspection and maintenance, as well as the dust collectors can be located outdoors in some cases. Another orientation that we see is utility spine. So this places all the dust collectors off the factory floor and out of the elements. Here we have a corridor where the electrical controls, gas plumbing, and dust collectors reside, keeping maintenance and inspection routines simple and effective. Localized orientation is the practice of using many small collectors paired with production lines in a facility. Some of the advantages of localized dust collection systems are the collectors can be prepackaged for export shipping, and moving lines around in the future or alterations can potentially be easier to manage. The drawbacks are that dust collection maintenance will be happening on the manufacturing floor. So there's a potential for airborne energy element materials such as lithium affecting product quality, environmental health and safety liability in the worker stations, and physical inspection can be overwhelming and an overwhelming task due to the number of collectors. This, however, can be mitigated with electronic monitoring. So here we have both centralized and localized on the same factory floor in a hybrid layout. As the economic investment in a gigafactory is immense and intended to operate for decades, we must factor in the need to update in the future. For those that design, for those designing for potential advances, they can consider hard ducting, the slurry mixes, coating, and slitting processes. Cell formation may change considering the pursuit of different technologies, like solid state, for an example, or future OEM requirements. In this case, one may consider using the smaller dust collectors to facilitate an easier changeover. Okay, so back to our system diagram here. The first component that we'll be talking about is the hood. This is a critical component of system design that will allow for airflow of containment and a collection of the fugitive dust. So a well-designed hood is going to minimize the amount of airflow that's required to effectively capture and control that contaminant where it is released in order to protect workers. It should be designed with good ergonomic principles in mind, and it should be compatible with the material flowing through the work area. It should also be designed to minimize the maintenance and other activities that may disrupt the process. So when it comes to assessing an existing system, a few common mistakes that we see are the wrong style of hood is being used, the hood is not located in an effective position, or you have inadequate airflow at the hood. In my experience with battery manufacturing, the dust collection system is often connected to a series of machines with built-in hoods or a simple dust port connection that only requires an airflow and static pressure for design. However, there are times when a hood is required, especially in the mixing and weighing operations where materials are exposed. The most common hood style is a closed capture hood, which relies on establishing a general flow pattern into the hood opening to produce a capture velocity at a specified distance from the hood. Here you see the 5 most common types of capturing hoods. The most common that we see are the slotted hood and the tapered hood in the field. So to minimize the air volume, the hood must be close to the capture point without disrupting the process. We have to remember, we only want the fugitive dust. We don't want to pull good product. As a general rule, a hood positioned twice the design distance from where the contaminant emission point occurs needs to draw approximately 4 times the amount of air to produce the same capture efficiency. So this is why proper design is critical, because more air means larger collection equipment, larger duct work, larger fan with higher horsepower, all of which adds to the capital and operational costs of the system. When determining the required airflow at the hood, the main design factor is called capture velocity. And this is the velocity that's required at the point where contaminant is generated to gain control of that contaminant and direct it into the hood. The main goal here is to keep the operator safe and keep the particulate away from their breathing zone. Capture velocities range from 150 to 200 feet per minute for light dust and 100 to 150 feet per minute for fumes. Both of these are prevalent in battery manufacturing, but just know that the capture velocity is often determined by the machine manufacturer and no additional hooding may be required. So whether you're designing hoods or relying on machine design, we want to avoid airflow extremes. Too much airflow at the hood or pickup may mean you're picking up good product rather than just nuisance dust. And since more energy is required to move that airflow, it could lead to higher than expected operational costs. On the other hand, insufficient airflow at the hood could require additional housekeeping measures to be implemented, and depending on the dust, may lead to an increased risk of exposure.
Hey, thank you, Neil. Just want to remind everyone to make sure you submit your questions. I see a few coming in on the chat here. So Neil and Chris will both be able to answer those questions at the end of the session. Chris, why don't you talk to us a little bit about duct design?
Sure, thanks. Once we design the proper hood to capture the contaminant, the goal is to move the particulate to the filtration systems through a series of ducts. The properly designed duct system should, one, pull the minimum airflow required at each hood. Two, maintain velocities required to transport materials through the duct to the collector. And three, you should do this using the least amount of energy as possible and minimizing any wear and tear on the duct components. A few common mistakes that I see are the wrong duct type, wrong size, and an unbalanced system. The minimum duct velocity is a critical design factor. It is the lowest velocity where all contaminant will be transported through the duct system. If you go below this velocity, dust could settle out within the ducts and cause other safety issues. Duct lines, no matter the size, must be full of air at the design conveying velocity to avoid settling out. This picture is definitely not what you want to see. For the light dust generated in battery manufacturing, the Industrial Ventilation Manual lists the minimum of 2,500 to 3,000 foot per minute and a bit less for fume, 2,000 to 2,500. However, typically we suggest increasing that to 4,000 to 4,500, especially since 4,000 is the minimum if the dust is combustible. If the duct velocity is too high, it won't create any safety concerns, but it will require more energy to move the air through the duct. Ultimately, this could impact the size of the system fan as well as create issues such as increased noise, abrasion, and wear and tear. Having a balanced system is one of the most important aspects to an effective dust collection system. It ensures you are pulling the required amount of air from each hood. To do this, the energy needs for each leg of the system at a junction must be the same. Neil, do you ever run into this in the field?
Yes, it's actually very common. Usually customers add a new piece of equipment to an existing system and don't consider the impact it has on the existing equipment. Originally these systems are designed for a specific number of machines or equipment, and as you add to that, like I said earlier, you can throw things out of balance pretty quickly.
Sure thing. And hey, for those on the call who are responsible for designing plants, if you know a customer is going to be expanding their process, there are ways to design future lines into a system so they don't have to sacrifice performance. But if a customer needs to add a line to an existing system, call in a professional to help. Don't just do it and expect the system to work because it may not. Okay, just a few quick pieces of advice when it comes to duct type. Rectangular duct is commonly used in HVAC applications where you are moving air only, but we don't want to use it in industrial application because dust settles out in the corners. It's okay for the clean air side though. When specifying industrial duct systems, make sure to call out round heavy-duty industrial ductwork. Most dust collection applications will use class 2, 3, and 4 ductwork, which are designed to SMACNA standards. Spiral duct is less expensive, and although I have seen it used effectively, it can leak air and could impact your design airflow by about 10%. If you do specify spiral duct, make sure it's heavy gauge and smooth on the inside. If spiral duct is used outside, this could provide a prime source for water to enter the ductwork and get into the dust collection system. So Use spiral duct with caution, and personally, I would hesitate to use it outdoors. Be aware that although flexible duct allows employees to modify the physical hood location to fit the process, it requires significantly more energy than traditional hard ducting. So if you are going to specify flexible ducting, we recommend minimizing it as much as possible. And you want to avoid branch entries with T's and hard 90-degree angles. Elbows, pictured on the left, should be 2 to 2.5 diameter centerline radius, except where space does not permit, in which case a 1.5 diameter centerline radius is acceptable. But if the elbows are mitered 90 degrees in turns, all the air must slow down, turn, and then speed back up. This creates a ton of turbulence, which adds more energy consumption and higher static pressure. Same thing for branch entries, pictured on the right, and you can see that a 30-degree angle is preferred. Neil, do you want to talk about the dust collectors?
Yeah, thanks, Chris. I may be a little biased, but I think the dust collector is the most important part of our system. You can have everything else right in the system, but if you choose the wrong dust collector, you'll run into unnecessary issues. So let's take a look at the dust collector design. So the overall objective of a dust collector is to deliver sufficient efficiency while operating in a predictable, stable, and economic fashion. Common mistakes that I've run into is someone using the wrong type of filter technology, incorrect sizing, either being too conservative or too aggressive, insufficient dust removal capacity, and then poor installation, which usually kind of falls in line with what Chris spoke about earlier with poor duct design standards. So as you can see from this chart, cartridge collector is a recommended type of dust collector for just about everything that Chris talked about earlier. Cartridge collectors are used for dry, fine dust, and they can be used for fume collection as well. There are some applications within battery manufacturing and recycling that require bag houses, such as high heat application, if you have dryers, material handling of bulky or fibrous dust. So although we're going to focus on cartridge collectors, just know that we offer more than 30 different types of collectors, and Donaldson's able to help customers with just about any type of dust, fume, or mist collection needs that arrive. Cartridge collectors are typically smaller and they've got a lower initial cost than a bag house. They work well in low and medium dust loads and fine uniform dry dust types, just like those found in battery manufacturing. They're continuous duty, which means the filters can be cleaned when the unit is running. They use plant compressed air and cartridge style filters. So in the photograph here, we have our Torrent Downflow Evolution, referred to as a DFE collector. And this is our best-selling cartridge collector and the one that I use most commonly in battery manufacturing. This is kind of a fun slide to see how we got to where we are today with cartridge collectors. So on the left is one of the first cartridge collectors that Donaldson introduced in the early 1970s. It was originally designed to replicate bag house collectors that contained vertically hung cloth filter bags with dirty air entering the collector below the filters. In the late 70s, we made some improvements with the inlet, which helped somewhat. But then in the early 80s, we had a breakthrough by rotating the filter cartridge orientation from vertical to horizontal, and by positioning the dirty air inlet directly above the filtration media. This change resulted in an incoming airflow pattern aligned with the desired final location of the dust discharged from the filter cleaning. Since gravity naturally directs discharged dust particles down towards the bin or drum at the bottom of the collector, the incoming air pattern of a downflow collector could now assist with the movement of particles to the containment vessel at the base of the unit rather than fighting against it. And then in 2014, we introduced our DFE. And what we did with this was move the dirty air entry. And we found that airflow capacity was increased by moving the inlet in a downflow orientation away from the filter media. So you have a dropout zone that allows the heavy particulate to fall from the airstream without ever touching the filter media, which made our filters last longer and allowed us to get by with some higher air to media ratios than we had in the past. So just like cartridge collectors have evolved, so have filter medias. Nanofiber was introduced by Donaldson in the 1980s, and the red dots that you see are representative of a single dust particle. And as you can see, the cellulose media on the left has many more areas within the media that allow particulate to load beyond the surface of the media itself. You've got both large and small particulate can embed deeper into the media. In that case, we call that depth loading, and it's not a good situation. That increases the differential pressure to a point where the filters need changed out sooner. However, if you look at the ultra-web nanofiber, the dust cannot easily get past the surface of that ultra-web image in the middle there. This allows for surface loading of the filter media, which improves the filtration and cleaning efficiency. So it's a lot easier to pulse fine dust off of the surface of a media rather than once it gets into the depths of the media. The most common filter that I recommend in battery manufacturing is Donaldson's UltraWeb. It's a MERV 15 cartridge media that filters down to 0.3 micron particle size. We have multiple options beyond the standard media for different types of dust and different coatings for fire resistance, dust release, and static dissipation. As I mentioned earlier, most battery manufacturing facilities are large, and with dust collectors located indoors, the exhaust is returned to the facility. I recommend a HEPA afterfilter. They are 99.97% efficient, and it's also becoming more and more common to see ULPA filters that have a greater filtration efficiency at 99.999. So we wanted to share an example of a recent install with you at a battery manufacturing plant. Chris, do you want to tell them about it?
Sure thing, Neil. The customer is a technology company focused on energy storage. Their main products are lithium phosphate materials, cells, power battery packs, and so on. They were experiencing challenges, including heavy dust loading, and they needed collectors located indoors. Also, we're experiencing some downtime and maintenance and fire mitigation problems and needs. We designed and installed a system with a DFE collector, UltraWeb anti-static flame retardant media, and fire explosion mitigation devices. The system is in use, and the customer is very happy with the reduced energy consumption and improved product yield rate that's they're able to accomplish with the efficient collector. As also, you can also see the customer opted for the centralized orientation that Neil spoke about earlier, and you can see all the dust collectors lined up down the wall if you look closely into that picture. So we'll talk a little bit about the fan now. When designing a system, the very last thing we do after completing all the airflow calculation is select and size the fan. Critical component of fan design is static pressure. It's basically resistance that the airflow must overcome due to system components. It's expressed in inches of water gauge. When we design a system, we calculate the total system static pressure so that we can size that fan properly. So here's an example from a recent system that we designed. The hoods totaled 1.5 inches water gauge. We'll just say inches from here on out. The ductwork, including straight runs of duct, elbows, and branch entries, totaled 2.5 inches. The filters and the collectors totaled 6 inches. The filter to the fan ducting was 1 inch. So the total system static pressure, if you add that up for this particular project, was 11 inches. The fan is like the heart of a local exhaust ventilation system. It has two responsibilities. First, a fan must deliver the necessary volumetric flow at the required static pressure to drive operations of the system. And since many dust collectors can operate with clean or dirty filters, the required airflow often has to be maintained over a range of static pressures. And secondly, the fan you select should be able to deliver the desired static and airflow with an appropriate energy efficiency at an acceptable sound level. For example, non-material handling fans located on the clean side of a collector are more efficient than material handling fans on the dirty side of the collector. Fan challenges generally fall into two categories: poor fan selection and poor fan installation. Fans are sized based on the system total static pressure and the required airflow. For example, let's say that I need to size the fan for the example I gave you earlier, 11 inches, and the airflow was 9,000 CFM. We use the system static pressure of 11 inches and line it up with the airflow of 9,000 CFM. And when we line those two factors up, we land between a torque backward inclined or TBI 25 and a TBI 30. When the lines intersect in between two fan curves, like they do here, we generally select the larger fan since you can always damper back the fan. So in this case, I would select a TBI 30. Neil, do you want to talk briefly about a few other design considerations before we answer the questions?
Yeah, let's touch on just a few things quickly before we get to the Q&A. So because battery dust can be a toxic and carcinogenic, an appropriate level of plant and personal protection is required when handling the filters and collected dust from the process. Pretty much all of the manufacturing facilities that I work with utilize a bag in, bag out process for handling dirty filters. I highly recommend putting this in your spec. Bag in, bag out allows the operator to load and unload the filters into the dust collector while minimizing dust exposure to the personnel and the facility. And we also have options for bagging out the collected material below the hopper. Another thing, as Chris mentioned earlier, the dust generated during battery manufacturing process may be combustible and pose a fire, flash fire, or explosion risk. Most of us are familiar with the fire triangles shown here. You got fuel, oxygen, and a source of ignition, and you have everything necessary for a fire. When the source of that fuel, in this case, our dust, is finally dispersed in the manufacturing process, it can lead to flash fires. And when that dust is then contained within a dust collector enclosure, the conditions are right for a dust explosion. So just out of curiosity, what's everyone's level of experience designing a system where the dust is combustible? If you could give us a thumbs up if you designed a system that has combustible dust and a thumbs down if you haven't, that'd be great.
Looks like we have some thumbs up, quite a few thumbs up. Neil?
Thank you. So as you know, this can be a pretty complex and complicated topic. We have webinars designed specifically around these hazards, and there is a good one in our on-demand webinar page that you can reference. There isn't a specific NFPA industry standard for battery manufacturing, so various processes will fall under the applicable general standards of the new NFPA 660, which is essentially just a compilation of all the individual industry standards to streamline things. I'll go over a few of the options that we can use to mitigate the risk involved. So first, we have inlet and outlet isolation. The dust collector ductwork must be isolated from the dust collector in the event of a deflagration in order to keep the event from spreading back into the process or return area. This is done typically with a mechanical isolation valve, but chemical isolation systems are more prevalent in battery manufacturing industry. Deflagration isolation. So our DFE collector was independently tested and the filters successfully isolated the deflagration and allowed no flame or sparks to pass into the clean air plenum. This is an important consideration when returning air back to a facility. Hopper isolation. That's typically a rotary airlock or a specially designed drum cover to prevent explosions from propagating through the dust collector hopper outlet. And then explosion venting on outdoor units and chemical suppression on indoor units help minimize or eliminate damage to the dust collector from an explosion before it becomes catastrophic. Again, this is a complicated topic, and if you have any questions, please reach out. We've got experts that can help. One final important consideration is specifying the electrical controls for the dust collection systems. These are considered the brains of the system, and they control things like the fan speed, the cleaning system, the monitoring. It's a very complex topic, and we are having a separate webinar just on electrical controls on May 4th, if you're interested in learning more about that. So just to reiterate, designing dust collection systems for battery manufacturing can be complicated. Each system and each facility is unique, and there are a lot of things that go into it. But that's what we're here for. We've sold countless dust collection systems around the world, and we have local support in your market. We're here to help make sure that we get it right the first time.
All right, thank you. Great job, Neil and Chris. We're going to finish up with some Q&A. Trainers, you can turn your cameras back on now. Just heads up, everyone that attended the session will receive an email with your professional development hour credit. If you don't get an email, sometimes it gets hung up in your junk or spam folder, and you're looking for that, you can email me and we'll make sure we try to get that off to you. So you should be able to get those. We'll also see here the QR codes you can see in case you missed that earlier in this session for the on-demand webinars, including the upcoming webinars if you're interested in attending those. And if you have any other follow-up questions, my email is on the screen here. You can send those off to you. We do offer in-person or custom lunch and learns if anybody's interested to do something in their local market. As Neil stated, we do have representatives across the country and across the world that can come in and work with you on site or look at your manufacturing facility and provide some consultation. So we'll turn it over to you, Amy. What is the first question?
All right, so first question, this one came to me privately. How long do filters last, and how do you know when it's time to change them?
Hey, Neil, I've got a little bit of info on that. So, I mean, since this is a new field, and I'd say like in the United States, people are designing very conservatively. So it's not uncommon for people to go, beyond a year with the filters that they've installed. And I would say those are the centrally designed systems where we have the larger dust collectors, outside and, abundantly sized. From Asia, the smaller dust collectors that go in amongst the factory floor, some of those I'm getting reports back that, they've designed them, maybe more in the 6 month range. I'd say this. If you take China, for example, and the abundance of battery manufacturing there, this is something that they have an abundance of. So maybe they run one shift or two shift. In the United States, we can't get enough of the batteries, and so we're commonly in the two shift or maybe even three shift. Very busy, can't stop. So I see that the conservatism in sizing is maybe affecting the life of the filters, but for the most part, you want electronic monitoring to give you a heads up. You want predictive maintenance in a high speed, high quality production, environment like battery manufacturing.
Thank you, Chris. All right, so our next one, let's see, this is probably for Neil. They're asking is if Donaldson provides designs for collection hoods.
Yeah, we have engineers that can help with hood design. In battery manufacturing, in my experience, most of the time, the equipment's already got a dust port somewhere in it or the hood's been designed. But if you run into those mixing opportunities where there's no existing hood, reach out to us so we can help you with that. Absolutely.
Thank you. All right, next question, is battery dust explosive?
I can answer this one. So The actual elemental dusts that go into batteries aren't necessarily, considered the most explosive dusts. Particle size can affect that, but the most important thing that anybody should be doing is do a dust hazard analysis. It's a economic, efficient way to take those dusts, send them to a laboratory, and they will give you the specific explosibility values, KST values of those dusts, and then uh, you can consult the authority having jurisdiction on what you need to do with those dusts. But a lot of people do ask that. The answer is test it. If you don't know where to send it, we'll be happy to direct you to some reliable firms who can do that for you.
Thank you, Chris. Our next question. So there was actually a couple of different questions about returning air back to the facility. Neil, are you able to see the chat box?
Yeah,
Okay.
I can see it.
So the first one, how would you address liability risks of returning filtered air back into the confined space?
So that actually plays really well into what Chris just said about the DHA. The part of a dust hazard analysis is not only the testing of the dust to understand what the chemical makeup is it explosive, but it's also they walk through a facility or walk through the plans to understand where there is risk and what can be put in place to mitigate those risks and minimize them. So, typically on a system where you're returning air into the building, you always have the HEPA after filter. And I noticed I was kind of reading above, there's some questions around dry rooms and
Yep.
the rooms where you've got more moisture. Um, I need to look into that, to be honest with you, on those, because it really comes down to how much humidity and how much moisture is in that room. These are dry dust collectors. They're not meant to be pulling any moisture into them. That being said, some of these filters hold up fairly well with minimal moisture in the dust stream, in the gas stream. But my gut tells me whatever is going into the collector is coming out. So if you've got humid air going into it, it's probably coming out that way as well. So if it needs to go to a dry area without the humidity, you would probably want to reroute that exhaust somewhere else.
Thank you, Neil. I know that was kind of a complicated one. That's sort of a complicated topic in general, I would say. So next question, this one came to me privately. We'd like to have a discussion with the Donaldson engineer to review a project. How do we arrange that? And is there a cost to doing this?
I'll answer that. So in North America alone, and just the United States and Canada, we have about 40 industrial vent trained territory managers who work with 300 affiliates across the United States and Canada. All of these folks are happy to come in and have a discussion and take a look at things with you free of charge. We're a handshake business. Dust collection is a local issue. Neil just answered a question about humidity. Hey, some plants have different humidities because they're located in different parts of the country, and these are very specific topics. So, no need to guess. You can have somebody come in, have a conversation about it. We do it that's what our job is. We do it all the time to help people, particularly in the design phase early on. Really most important, the design phase. Yeah, we're happy to do so. So, please reach out. We'll
Thank
get
you.
we'll get you a person.
Thank you. All right, so this is Chris, probably this is for you too. So it's about the training in June because you're going to help with that one as well. They're wondering if does it include filters for battery recycling instead of production. So could you talk maybe a little bit about the training that you're going to be leading, the webinar for June?
Yeah, absolutely. With battery recycling, we have lithium-ion battery recycling. We have really basically electrochemical little bombs when they bring them into a recycling facility. So we talk about a whole different type of process where they have to be discharged, decomposed, shredded, whatever way they are. And all of the materials that we talked about earlier are all the materials that we'll be dealing with, but it's just a different set of circumstances because it's going to be maybe a moist dust different types of challenges, and you know, it's a different field altogether than the putting them together. And I would say that you know, we emphasize safety, but yeah, we'll go through recycling processes. You know, I've seen a dozen different recycling processes and flow charts and things like that. We'll go through the flow chart and all the machinery involved in that. It's a unique field for sure.
Thank you. All right, so this one's probably for Neil. What would you say is the most common issues with dust collectors in the business? Issues like holes in the filters, breakdown of the fan. Like, what are some of the more common issues?
I would say the most common issue that we see is around the cleaning of the filters. So these systems are typically designed to clean on demand. So once the differential pressure hits a certain high set point, the pulse cycles will begin and they will stop at a low set point. Um, that's something that needs to be managed by the maintenance team and monitored. It's very common that they go out, you know, it comes set at 4 inches for a high, 2 inches for a low. And once it exceeds that 4 inches, it's very common that they forget to go in and change the high and low set points. These are designed to run up to 6 inches of differential pressure on the filters. So that's a common issue we see. Another common issue is the pulse valves themselves. It's a wear part. There's a diaphragm in there that wears out over time. And as that wears, if it becomes cracked and you don't have that same seal, you lose cleaning energy that way, which will obviously impact how clean the filter gets, which keeps the differential pressure higher as well. So really, most of the common issues are just maintenance issues. And Donaldson's come a long way to helping our customers in that with the new smart collectors. So every collector we sell now comes with an IQ monitoring system where they can go in and set a dashboard that says, hey, once I've hit this certain differential pressure, I'd like to get a notification, and they'll get an email. Whoever at the plant is on that email chain will get a notification that says, hey, DC4 has reached high differential pressure. Someone needs to go make some changes to the controls. And that's eliminated a lot of the troubleshooting back and forth. The other nice thing about that is it allows them, if they want to share the information with me, to go into the dashboard and we can kind of look at the trending information and understand what's going on and do some troubleshooting over the phone. If they happen to be, hours away, we can't get there right away.
Yeah, technology's really made troubleshooting a lot easier than it used to be, that's for sure.
Yeah, absolutely.
So, Neil, this one's probably for you too. Would you say that your equipment is intrinsically safe?
Yeah,
I'm assuming, I think this came in during the combustible dust conversation.
yeah. So the
That's fair.
controls have intrinsically safe landing spots, and the wiring schematics outline which ones need to be in their own ISB so that everything is up to par as far as an FPA is concerned.
Thank you. And let's see, next one. Do you have, they're looking for instructions for bag in, bag out on a DFE.
We do,
Okay.
and I'll be completely honest with you. They're in the IOM when you
Okay.
buy a collector. Uh, We've got some videos that we can send that better illustrate how that works. I think the instructions in our IOM are kind of tough to read and understand how it works, but when you watch the video, it makes perfect sense.
Okay, so we can reach out to this individual and get some information for them. So
Yep.
thank you. All right, so next question, do battery slurry or other steps present any special challenges like corrosion that require specialized collectors or ductwork? Or perhaps grounding is more important than other applications? The battery slurry.
VOCs, odors that can be smelled harmful to humans. Donaldson does not capture VOC, but if the process is not sealed, every process is, dependent on the manufacturer of the equipment. You can mitigate VOC through carbon filters if needed, and potential thermal oxidizer if it's a big concern or a big capture. So that's what I would anticipate. And yeah, it could be flammable too. I don't know, Neil, you have anything on that?
Yeah, I was just gonna say, typically, what we see most is galvanized ductwork. There are certain situations where they may choose to specify a stainless steel duct because of the corrosion concerns. But to be quite honest, this is such a new industry that we haven't really seen situations where they're completely chewed up from corrosion yet. And the ones that are in the field and are working aren't showing any signs of that so far. So I think to answer that question, a lot of it comes into if the system's designed properly and you've got the right duct velocity and the right capture velocity at the hoods to keep that moving through to the filters should capture most of that.
Thank you. All right, so this is a generic question. Have you ever run a filter dust collector discharge back into a building through an energy recovery ventilator?
I have not.
Me neither.
Quick answer for that one.
I'll look into it though. We'll
Yeah,
study that.
exactly. Yeah, we can look into it and get back to you.
It sounds like a very compelling thing to do.
They're both like, ooh. All
Good
right,
idea.
so we'll make sure to follow up with you on that one. So that we are just about at time, and that was our last question. So thanks to everyone for joining us today. Thank you so much to Neil and Chris and John as well. John's information is on the screen if you would like to get in contact with us and if you had any additional questions. And this recording will be available on our website as soon as possible. We hope you have a great rest of your day. Thanks, everyone.
Thank you.
Thank you.
Bye all.